Welcome to lecture 18. So I will continue discussing that asymptotic equipartition property and prove a theorem and certain results, so which will be important in understanding the universal encoding scheme. Not only that, if you understand this asymptotic equipartition property here properly, later on when we will talk about joint typicality, it will help in our understanding of capacity and channel coding. So this asymptotic equipartition property, of course I will be proving the theorem, but before that let me first intuitively give one example and show what this term asymptotic equipartition property mean. Partition property. So why equipartition? So it basically, so what it tries to say, that if you draw x is like x1, x2, these are IID random variable and everything follows the PMF Px. Okay, then this is for one random variable, PMF for one random variable, for random variable x. These are the instances. Okay, then we say that the joint distribution of n joint PMF, which is p x1, x2, xn, we say that this will go towards this value. So this will go towards this value, 2 to the power minus n hx, irrespective of basically this will become a constant. Okay, now what does that mean? So if I look at these vectors, so x1 to xn vectors, so every random variable can assume one of the capital M values, right? So suppose x, so the range set, we can say x assumes values in this set, which is essentially this a1, a2 up to am. One of these values are obtained. Okay, so this particular sequence x1 to xn, it will assume some it will be a vector, so which I am naming as to be x superscript n, which is basically a vector which will be having value like x1, x2. These are the values the random variable assumes, and each of them will be one of these. So this takes values from this set, which is the Cartesian product of the, so I can say this is the Cartesian product of n times of the set. Then I say that assuming a particular value of this xn, so if that xn is typical means when the PMF of that particular sequence is close to this. That is the definition of typicality. So typicality by a epsilon n, I mean that when this p x1 to xn, which is basically your p x superscript n, that probability should lie between two limits. One is minus n hx minus epsilon, and another is the 2 to the power minus n hx plus epsilon. So if the corresponding PMF, joint PMF value resides within these two values, then we will say that that particular sequence xn, that belong to this typical set. So typical set is basically like a set of those sequences. Let us take one example of such typical set. What does it mean? Okay, so here also. So example, let us assume the coin toss experiment. So you are having head and tail, and I define the random variable to be 1 if head falls, 0 if tail falls. So this is a Bernoulli random variable. And let us assume the probabilities are, so probability of head, or I can say probability of x is equal to 1 is say 0.7, and probability of x is equal to 0, or probability of tail is say 0.3. Okay. Now I say, suppose I am drawing this random variable, this Bernoulli random variable, total n is equal to 10 times. Okay, this very number I am drawing the random variable. Basically what I am doing, I am basically tossing the coin n times, n is equal to 10 times. Now what are the possible outcomes? So the vector xn, which is basically a sequence of ones and zeros, so a string of length 10 where every entry is 1 or 0, 1 for head and 0 for tail. So it can assume the value in this set 0, 1 to the power 10. So what are the possible total number of cases? There are 2 to the power 10 such sequences which are possible. So the cardinality of this set, this I am naming to be this. So the cardinality of this set is essentially 2 to the power 10, which is 1024. Okay. So many number of sequences are possible. So that you can see that the sequences are basically starting from 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. So 10 zeros to 10 ones. So there are how many such sequences? 2 to the power 10 sequences, 1024. But out of that, we know from our understanding of probability that these are very much unlikely. So sequence of 10 zeros or sequence of 10 ones, these are very much unlikely, because our law of large number, of course 10 is not that big, but even then if you toss the coin, you will see that you will not get all of them to be the identical values. You can change it to 100. I did not take this 100 because I am not going to write it, but even if you take this to be 100, the set side will be 2 to the power 100. Okay. Now the meaning of probability, even from a frequentist point of view, frequency distribution point of view, it means that if you draw the random variable 10 times, you expect that the head will fall 0.7 into 10, that is 7 times, and tail will fall 3 times. So the random variable 1 will take value 1 typically 7 times, and the random variable will take value 0.3, random variable will take the value 0 typically 3 times out of the 10 tosses. So these sequences, so where that's the notion of a school level probability, that you are tossing the coin 10 times. If you are getting 7 heads, that means probably your head probability is 0.7. If you are getting tail 3 times, that means the tail probability is 0.3. That is the understanding when n is large. Okay, your weak law of large number tells that only. So if your sequence is say of this sort, say so I tell that 1 is 7. So suppose I am getting something like 1 1 1 1 1 1 1 0 0 0. That is a typical sequence. I can get it 1 0 1 0 1 0, then 1 1 1 1. That is also a typical sequence. If I get something like 0 0 1 1 1 1 1 1 1 0, that is also a typical sequence, as long as there are say 7 ones and 3 zeros, they are typical sequence. But not only that, even if you change a little bit, that will still be within typical, because in the typical set is a function of epsilon, so we allow some epsilon also. But right now let us not allow epsilon, and let us see what are the probabilities of occurrence of this. Since every coin toss is a random variable, independent random variable, what is the probability of occurrence of this? You know how from Bernoulli to binomial expansion, like binomial random variable, that derivation. So from there you know how to compute the like joint probability of occurrence of this one. So this will be P into Q into P into Q into P into Q into P into P. So this will be P to the power 7, Q to the power 3. The ordering does not matter. So which is 0.7 to the power 7 into 0.3 to the power 3, isn't it? And you see all of these sequences, all of them will have the same probability. So the probability that there will be like number of 1 is 7 and number of 0 is 3, the probability will be same. This is the probability. Now what is this? Let us observe, let us try to understand this particular quantity. So this quantity is essentially 0.7 into 0.7 to the power 10 into 0.7 into 0.3 to the power 10 into 0.3. I can write like this. So this I can write as 2 to the power log of this. So which I can write as 10 into 0.7 log 0.7 to the base 2 into 2 to the power 10 into 0.3 log 0.3. So I can multiply them together. So this will be 2 to the power 10 into 0.7 log 0.7 plus 0.3 log 0.3. So I can take a minus out. So it will be minus 10 into, this will be minus 0.7 log 0.7 minus 0.3 log 0.3. What is this? This is the entropy of the Bernoulli random variable. So the Bernoulli random variable which I have defined over there, the entropy of this is this. This is the entropy. So this is equal to 2 to the power minus 10 into hx. This multiplied here. So this is minus 10 hx. So you can see that all of them are having equiprobability. All of these so-called typical sets, typical sequences, they are having the same probability. But even if I perturb a little bit, so probably allowing 8120 or 6140, probably that is also fine, because if as long as my probability is within that tolerance range of epsilon, I don't mind. N is probably not a good idea. It will be better if I take some 100 or 1000, something like that. N, then you can see that that epsilon value will be really small, and even if you allow a little bit, so the probability will not be exactly same of all the typical sequences, but it will be within that tolerable range of epsilon. Okay, so this is the idea, and how that probability of typicality is related to the entropy. This I have just shown with this simple example. So next I will continue proving the theorem of asymptotic equipartition property. Why equipartition? Equipartition means that the so-called these typical sequences, they are the most likely sequences which will happen. So the other atypical sequences like all 0 and all 1, they will not happen. So these will happen, and in the next theorem I will just prove that the probability of occurrence of a typical set, I will prove that. I will show that that is arbitrarily close to 1, and the atypical set, that will be arbitrarily close to 0. So asymptotically, as n increases, you can see that arbitrarily the sequences which will happen, the vectors which will happen, which will actually occur, they will have equal probabilities. So that's why it will partition the like possible sequences with equiprobability. That's why it is called equipartition asymptotically. Asymptotically means as n tends to infinity. So as n is large. And if you write a simple MATLAB code, you can actually observe it, that you can draw some random variable and you can do that experiment. You draw some random variable using uniform distribution, and then you like map, you design the Bernoulli random variable with say p is equal to 0.7 and q is equal to 0.3. Then draw that Bernoulli random variable for some large number of times, say 1 million or something like that, and then see that if you draw that random variable say 1 million times, multiple times, even if you can start with say 1000 times, and if you draw it, you will see that most of the time you are getting like 700 heads and 300 tails, something like that. So the order does not matter, but that will typically happen. It can be from 700, it can happen 701, 702, etc. So, but it will be within that typical set. It will not go beyond that. Okay. So I will not now go towards the theorem. So the theorem is, we say that if xn, which is your x1 to xn, it belongs to the typical set, then the following four are correct, which is, first one is basically the definition itself, log p x1 to xn is between hx plus epsilon and hx minus epsilon. The second is the probability of the typical set. This will be greater than 1 minus epsilon for some large n0 epsilon, I can write. As long as n is large, that is true. Third is the size of the typical set. This is important because if I ask you that what is the size of the typical set such that there will be 7 ones and 3 zeros. So how to answer that question? So the like it is basically choosing 7 ones from 10. So it is 10C 7. So that is the size 10C7. Now whether that is equal to 2 to the power 10 hx, that we will see, because over here I am saying that this will be bounded by these two numbers, 2 to the power n hx plus epsilon, and upper bounded by and the lower bounded by 1 minus epsilon 2 to the power n hx minus epsilon. Both are for some large n. Okay, we'll prove these four statements. First one, there is nothing to prove, that is just a definition of typical set. Okay, nevertheless check it. Second one is important because I want to compute the probability of the typical set. Okay, so so how to compute the probability of the typical set? So from our weak law of large number, if I just apply the weak law of large number statement, that statement in the last class I have done it, you please check. So it says that probability of minus 1 by n log p xn minus hx, this is greater than epsilon, is less than delta. That is the understanding for some large n. This is the expression of weak law of large number. Okay. Now this, if I break down, if I write like take hx this side, that is same as saying minus 1 by n log pxn is okay. I will not take the greater one, rather let me take the less than one first. So if I take it within less than epsilon, then that will be greater than equal to 1 minus delta. Obviously, if this is this statement is correct, the other statement is 1 minus delta, greater than equal to, obviously this is close to 1, the probability is close to 1. Okay. So this I can write as probability of minus 1 by n log Pxn will be less than Hx plus epsilon, isn't it? And greater than Hx minus epsilon, isn't it? So that's the expression of this. This will be probability and will be greater than 1 minus delta. Now what is this? What is this definition? This definition is nothing but the definition of the typical set, because for typical set this expression is correct, what I have just written. So that is the first statement of the theorem. So whenever this is correct, that is basically the typical set. So this is the probability of the typical set. So I get probability of the, I'll write in this page, yeah. I'll get probability of the typical set, occurrence of the typical set, to be greater than 1 minus delta. Now like delta is nothing, there is no like true meaning of delta. Delta is any small number, so I can choose that delta to be this epsilon. So without loss of any generality, I can fix delta to be equal to epsilon. Then I get the result, which is probability of A epsilon n is greater than 1 minus epsilon. Why I fix this particular thing? Because in the next statement it will be obvious. Okay. So the second one is proved, as long as that n is greater than some n0 epsilon. That is coming from the statement of the weak law of large number itself. Okay. The third one. So for the third one, I will basically compute the total probability. So from total probability it will come. So total probability is for the sequences. It is basically probability sum of all the sequences when the sequence belongs to the complete set. Okay. Now this can be broken into two parts. One is the, suppose this is your the complete set, out of which there is some typical set, and the rest is the atypical set, which I can write as bar or something like that, complement, and write as complement. So in these two parts, so I can like partition the probability into those two parts. So one is when it belongs to the typical set, another is when it does not belong to the typical set, belongs to the or does not belong to the typical set, or belong to the complement. Okay. Now when it belongs to the typical set, I know that okay, I can disregard this for the time being. So I can say that this is greater than equal to Pxn. Xn belongs to the typical set. I am going for the like I'll try to show the upper bound first. Yeah, the third expression is the upper bound. Yeah. So then I can disregard this. These are positive quantities. So if you remove that, so 1 will be greater than this. Okay. Now every probability, I already have the expression of the probability here. So the probability here is basically greater than Hx minus epsilon. No, probability is not greater than, probability is let me just write down from here. So from there we got that probability of xn, that will be greater than 2 to the power minus n hx plus epsilon. Yeah, that's the expression. So from this side I will get, so n into hx plus epsilon, when you swap the minus it will be greater than, so greater than, then log will be 2 to the power. So that's the expression. The other expression will be Pxn is less than 2 to the power minus n hx minus epsilon. That's the definition of typicality actually. So the first result I will use here. So this will become greater than equal to summation 2 to the power minus, actually equality sign does not matter. I can just put greater than. It does not change anything. So minus n hx plus epsilon. Now you see that these are for all xn in that set, and this is a constant. This particular value is a constant. It does not depend on a particular choice of xn. This is constant. So this goes out. What remains? The size of the set, which is the cardinality of the set. So now from here I can get the size, I can get the bound of the size. So I can write from here. So the bound, the cardinality is less than 2 to the power n hx plus epsilon. It goes this side. Okay. So I get the upper bound as long as n is large for all n. So this is like the number. So in that example, if I ask you to compute for a given epsilon, you can see that it will be close to this number, 2 to the power n hx. So you can see that the size of the typical set is this, and each element in that typical set is having this probability. Multiplying these two will basically give you unity. So it will ensure that with one probability that typical set will happen. Obviously, from here I can see that. However, next is the fourth one, so which is the lower bound. I will prove that as well. So the proof of the lower bound is page number 5. So again, probability of a e n, this I know that this is greater than 1 minus epsilon. Okay, we have already proved in result 2. The probability, the typical set probability is 1 minus epsilon. So I can say that 1 minus epsilon, that is less than probability of AEN, which I can write as the probability of all xn such that those xn belongs to this set, isn't it? Now Pxn, that I already obtained. Just a minute. Yeah, in this side I have just written that Pxn is less than this. So this value I can just inject there. So this will be less than 2 to the power minus n hx minus epsilon. So that I obtain. So xn belongs to AEN. So this is a constant, it goes out. So this will be equal to minus n hx minus epsilon into the cardinality. So from here I obtain the cardinality of AEN is greater than 1 minus epsilon into 2 to the power minus n hx minus epsilon. So I established my 4 results of the particular theorem. Okay. So this is some good result. Next I will tell you that how we can exploit these results to describe some code. So I want to develop some code which will exploit the typicality. Okay. So what I want to do, I want to basically so some encoding scheme using typical set. Why this like typicality is becoming useful? Because suppose this is the complete set, and out of that this is a typical set. Okay, AEN. Now if with one probability that something from this typical set happens, then and if all the members of that typical set are equiprobable, then we know that we can just do fixed length encoding. So fixed length encoding will work, and then that will give me, because the size is, what is the size? Around 2 to the power nh. So the size of this is around 2 to the power nhx. That's the size. Each one, each symbol is having probability 2 to the power minus nhx around. So many typical sequences. So how many number of bits are required? nhx bits are required. So for n symbol sequence, you need nhx bits. So for every symbol, what is the typical bits which will be required is hx. So I want to go towards hx. I remember the mean length of encoding, so which the lower bound is hx. So I want to approach hx. So here it is showing that it is actually approaching hx. So but if you want to do fixed length encoding for the entire set, then it will be like log of the cardinality, log m, so many number of bits per symbol. That is the understanding, right? Let me prove it comprehensively. So what I will do for the typical set, AEN, I know that the length xn belongs to the typical set. The length assigned will be less than equal to n hx plus epsilon, and suppose this nhx plus epsilon is not a integer, then you can put a ceiling, so that can add 1 bit to it. Okay, now you can put a flag, one extra bit, that put some flag bit. That flag bit is, which I am putting to be the MSB, the most significant bit. So I will put, if it is 0, I will say that this is typical, and if this is 1, then I will say that this is atypical complement. So the first bit will decide whether it is typical or it is atypical, and both the typical and atypical sets will be encoded differently using different number of bits. So for the typical bit, typical sequences, I will use these many number of bits, that is the maximum number of bits which will be required, and that extra bit I will add, so it will be another bit which will be the flag bit. And for the atypical set, AEN complement say, so I will say that the length of such sequences for the code belonging to AEN complement, it will be less than n log of capital M, so the cardinality, and I am using again, if this is not integer, then I will put 1 bit for that and 1 flag bit. So this will be the flag bit, the MSB. Okay, so that's the length. So now let us compute the expectation of length. So expectation of length will be basically summation p xn into lxn for all lxn. That I will partition into the two sets. One is typical, another is atypical. Pxn lxn plus Pxn lxn. Xn belongs to the atypical. Okay. Now I know the probabilities and I know the lengths. So here, what is the probability? So I can put the upper bound. Upper bound is the probability is basically if the length is this, the remaining thing is the probability of belonging in the typical set, isn't it? So this I can write as less than equal to n hx plus epsilon plus 2 into probability of the typical set. I can write like this. Okay, here also I can write because these are fixed length in codes, so this remains, this becomes constant, that goes out. Whatever probability is left is basically probability of the set. So n log plus 2 into probability of the atypical set complement. That's the probability. Now I will use the upper limit. So this, the probability of the upper limit of this is essentially 1. One thing I can see that this 2-bit, 2 into probability of this plus 2 into probability of this is basically 2. So this 2 I can take out. So this is 2 plus what remains is n into hx plus epsilon. This is the first term into this, the upper bound is say 1, plus log of plus n log of this into the other probability, the atypical set probability. But for the typical, I already got one expression, that is the probability of typical set is greater than equal to 1 minus epsilon. So the probability of the atypical set is less than epsilon. So this probability will be less than epsilon. So that I can apply here. This is epsilon, isn't it? This is coming from the fact that probability of the typical set is greater than 1 minus epsilon. So the probability of the atypical set will be less than equal to epsilon. So that we have put, this is the less than sign. Now rearrange. So if you rearrange, you will get 2 plus, or I can take n common. So if I take n common, it will be hx plus epsilon plus epsilon log the cardinality plus 2 by n. Now you observe that this entire thing is small because epsilon is arbitrarily small, this is arbitrarily small, and n is large, so 2 by n is also arbitrarily small. So this I can write as n into hx plus epsilon dash, where epsilon dash is epsilon plus epsilon log m plus 2 by n. This is how I define the epsilon dash. So I get that the expected length is less than equal to n hx plus epsilon, some small value, yeah. So clearly you understand that for like every symbol it will be around hx. So I can write that expected of 1 by n lxn per symbol, it will be less than hx plus epsilon dash. So with this I conclude my topic today, as long as n sufficiently large. And this can be a encoding scheme where you divide it into typical and atypical set, and then you can encode such that you are forced to get it within the entropy bound. And this is pretty tight bound because this is arbitrarily small. Okay. So I stop today. Next class I'll be talking about the Zibbe-Lempel algorithm. So which will be the universal algorithm. Okay. Now what is my scheme after that? So this source encoding will be done. Then I'll go towards modulation, the signal design for real digital communication. So we'll start with some baseband communication first, then we'll go to the passband. Okay. This information theory is extremely important. Whatever you are learning now, please learn, because this will come again and again. So I will not reintroduce everything, because the formally I have introduced the rigorous mathematics for whatever is required. These things will come back again and again. So whatever you have learned during that epsilon entropy, that thing will come. Whatever you have learned during the finiteness of band limited and time limited signal, that will come. This asymptotic equipartition property will come, mutual information will come, so everything will come. So please go through all the lectures, and I can assure you that if you listen to these lectures carefully, you will learn the topic, because I am following some number of books, not one book definitely, and you will not get the entire thing in any single book. So please follow. There will be tests, there will be assignments, don't worry about that. But initially I thought about giving too many assignments, but then I understood that you are third year second sem, you are not anymore like high school students, such that I have to monitor every day whether you are learning or not. As long as you are listening to it, you are following it, you are following the material, you have my transcripts, you should be able to understand whatever is happening. Okay, so please follow. See you next Wednesday. Bye.